Okay, through most of the YouTube video here, I've tried to avoid being uh, very technical, but we have a couple of questions, open questions or issues that I do not know how to answer without going to the actual trigger pulse waveform. So that's what we're going to do in this addendum. Okay, the purpose of all of this is to understand why we don't get any spark at all below a certain RPM, a threshold RPM. And we want to also understand why the spark did not occur when the magnet was centered on the trigger coil. We were very careful to set those up and center them that way, and then the spark occurred usually sometime ahead of that. And then the third thing we want to know is we changed the polarity and we got a dramatic change in the timing, the ignition timing. So I think it would be good to know why those things are happening. The uh, the uh, the topic here is really about magnetic induction, and in magnetic induction, it's the changing of the magnetic field that induces the voltage in in the coil wire. So the higher the rate of change, or the faster this change uh, of the magnetic field, the higher the voltage in the coil. And the other thing that it would be is that the higher the RPM, then the higher the voltage in a coil. So we're going to use the RPM of the flywheel to control the ignition timing. The discussion here is going to be in the form of a graph. And um, the graph and the horizontal dimension of it is time, moving from left to right, and then the uh, vertical dimension of is the volts, the voltage output from the trigger coil, and the positive voltage would be go from a zero line uh, up upwards. So we're going to be using an oscilloscope which connects to the trigger coil output and produces this graph for us. One might think that the output pulse from the trigger coil just looks like a positive pulse. The voltage is along by zero, the magnet comes by, and bingo, we got a positive voltage which goes to the control module to fire the spark. This, however, is not the way it is at all. I used an oscilloscope attached to the output of the trigger coil to make us a picture of the actual trigger waveform. And it's shown here. If we take the yellow line and we go to the far left, we can envision the magnet is somewhere quite distant from the trigger coil. And as the magnet moves to the right, it's approaching the trigger coil. And as the magnet gets about 22 degrees away from the trigger coil begins to sense its presence and its motion, and it begins to generate a voltage which creates the positive pulse for the ignition. Now, as this goes on until the magnet reaches the center of the trigger coil, and at which time there's a dramatic reversal in the output voltage from positive to negative. Okay, and as the flywheel continues to rotate, the magnet now is moving away from the trigger coil, which causes us to have a negative voltage. Now we have some funny things going on here that I haven't seen before. Usually the positive pulse and the negative pulse are about the same height, but there's an extra little squiggle going on to the right side of the waveform. And if we follow this on the flywheel, the position, this is where the OEM magnet is. So what the trigger coil is doing is sensing the OEM magnet, even though it's pretty far away and it's not even on the back of the flywheel, it's up on the face of the flywheel, but it does sense it, and we get a small positive pulse, and as the magnet continues to move away, we get a negative pulse. So this is the effect of the OEM magnet. At this point, I left the power to the ignition turned off, so we did not get any radio frequency interference into our diagram. What I did is I turned the power on for the ignition, and one of the first things we can see is there's a huge spike occurs almost on top of the positive pulse from the trigger coil. And for the control modules we're using, which are the newer design types of, they're quite a bit different than the original 1980s Chrysler control module, and it appears here that they trigger the spark on this transition point between the positive pulse and the negative pulse. So that's pretty convenient. Now I did put a timing light on the trigger coil, and it did show that it wasn't centered on the trigger coil, but it was a little bit to the right of the center of the trigger coil. But it did show the magnet right there at the trigger coil. The other thing that's important here is if we look where we're getting the input from the OEM magnets, which are still on there, we don't see any bonus sparks or anything. So this is good, and it probably did a good job. And if we put the oscilloscope and all that stuff aside and take a look at the actual spark location with a timing light, we can see that what I found on the setup on the simulator was that the spark was occurring as the magnet was at the trigger coil. It's very close to being centered up here. This is different than I have found in the past, and fortuitous, and it makes it pretty simple in our planning for the timing for the spark. The issue that I want to address in the appendix is the one where we got a shift in the ignition timing when we reverse the polarity of the trigger coil. So in all of the previous pictures, I had the positive pulse arriving first, then followed by the negative pulse. And to change this, I switched the wires on the trigger coil to ground the blue wire, and to put the yellow wire going off to the control module. The reason I had it the way we did in the previous pictures was the magnet on the flywheel is actually reversed, so from what my normal standard way of doing things are. So what we can see here is that the voltage comes in and we get a negative spike, and then that rapidly rises when we reverse the polarity to go to a positive, and then on the positive spike it comes down the slope of the positive pulse, and about halfway down, bingo, we got a spark. In the previous pictures we got a spark in about the same place, but that descending point on the positive pulse happened to be in the transition from the positive pulse to the negative pulse. But so the actual trigger point is occurring at the same point. Now this turns out that this point in the waveform is about retarded about 10 degrees from the previous trigger point, which had the positive pulse and used the positive pulse first, and use the voltage reversal as a point in the waveform, which is much steeper than the portion of the waveform we're using here. So this is a delay in the spark about 10 degrees, retarded, and we can control this very easily by reversing the wires on the trigger. And most cases, I think we would rather have it with the first case with the positive pulse first. But if we were having trouble with the spark being too much advanced, we could reverse the wires on the trigger and retard the spark by about 10 degrees. Okay, let's put the oscilloscope world out of the way for a while and take a look at the real world and see what's really going on using a timing light. And if we put the timing light on the trigger coil in this configuration, what we'd find is, or what I found was the timing has retarded. The magnet is about 7.5, maybe 8 degrees off to the right of the trigger coil, whereas with the other configuration, with the wires reversed, the magnet was at the trigger coil. So it's very important for you to use a timing light to make these checks, so you can verify what the configuration you have, and it's a lot easier than trying to keep track of which way the magnet's facing and which way the wire is turned and which wire is connected to ground and which one to the trigger coil. So if you hook it all up and just put the timing light on it, it'll tell you whether you've got the timing on target on the trigger coil or whether it's retarded. Under some conditions, you may want to retard the spark a little bit. For example, if you had a knocking condition that you wanted to correct, you could very easily just switch the wires and retard the spark. So the way I arrived at this 7.5 to 8 degrees was I counted the number of teeth on the flywheel shown in the picture here. There were 121 of them, so I divided 360 degrees by the 121 and got very close to 3 degrees per tooth. I noted earlier that as the RPM increases, the trigger voltage increases. So what I have here are 4 different RPMs, and I use the oscilloscope to actually measure the positive peak voltage. So it makes both of these measurements as well as takes the pictures of the waveform for us. So the first one on the top is at 150 RPM, and the peak positive voltage there is like 0.113 volts, and there's no spark. We move to the right, the top right, and the RPM is up to 200 RPM, and the voltage increased to about 0.2 of a volt, and this time we have a spark. Now the spark may be added to the computed voltage for the pulse, so that doesn't seem to be a problem if there's a negative going pulse, but for the positive going pulse here, it seems like it is. It's also a very low RPM for getting an advanced spark, so I have no idea what I set the air gap at, but it obviously needs to be a little bit wider. So down on the bottom left, we have the RPM up to 400, and we have a spark here, and the peak voltage now is increased to 2.32 volts. And let's see, then on the right, we go up to 600 RPM, and the voltage is increased to 3.2 volts. And both of those cases, we have a negative going spark for the spark noise. In summary, then, below at the RPM, the threshold of the trigger, we can create the condition where we have no spark, which is very desirable when you're just trying to start the engine. And then as the RPM comes up and we get the initial top dead center spark, the engine starts It'll run on that briefly, and when the engine picks up some more speed, the RPM will increase the trigger voltage, and we can get the advanced spark. I have a strong favoritism for this type of ignition because it gives us the ability to build an ignition to the timing characteristics that we really want. Okay, I think we did a real good job of locating the new trigger magnet on the back side of the flywheel and in rotation before the OEM magnetomagnet.